A computer mouse without a scroll wheel is ridiculous. It's like having a TV without a remote control. Yes, you might be able to make it work, but is it really worth the effort? Well, in this episode, we're going to explore the scroll wheel in detail. First, we'll examine two different technologies used to measure the direction and speed of rotation. And after that, we'll see what causes some to have a stepped or clicking motion versus spinning smoothly. So let's jump right in. This video is sponsored by PCBWay. More on them later. Scroll wheels commonly use either optical rotary encoders or magnetic rotary position sensors in order to measure rotational motion. They're functionally equivalent in that they both measure rotation, but technically different, as one uses light and optics while the other uses magnets. Let's first explore the optical rotary encoder. It has three key components. First is an infrared LED that emits light and a lens that focuses it. Next, there's a pair of optical sensors that detect the light. And finally, mounted on the inside of the scroll wheel, there's an encoding disc with 48 equally spaced spokes, which rotate when you spin the wheel, kind of like the spokes of a bicycle wheel. The key to the optical rotary encoder is that, as the wheel is rotated, the light emitted from the IR LED is intermittently blocked by the encoding disc. The light that makes it through the slots between the spokes reaches these two optical sensors and is converted into an electrical signal called a pulse wave or pulse strain. And with every full rotation of the wheel, each sensor sees 48 pulses of light, resulting in 48 electrical pulses. Let's spin the wheel rather quickly. Within each hundredth of a second, the sensors see 12 pulses of light, and using the generated pulse strain, the processor calculates that the wheel is spinning at 25 rotations a second, and then sends this information to the computer. The information is not speed, however, but rather the angular distance measured in degrees and the direction the scroll wheel has traveled every hundredth to 1,000th of a second. This angular distance and direction can then be used by the operating system and its software to know how far up or down to move in a website or application. But how does the scroll wheel know which direction it's rotating? Well, the two sensors are spaced next to one another, and depending on the direction the wheel is rotating, one sensor sees the light before the other. For example, if you scroll the wheel down, the pulse train from the two adjacent sensors will look like this, whereas when you scroll the wheel up, it will look like this. By the way, this is technically called an incremental quadrature encoder. It's called an encoder because the term encoding means to convert one form of data into another form, and in this case, we're turning mechanical rotational motion first into an electrical pulse train, and then into speed, distance, and direction. Let's move on to the other type of scroll wheel, the magnetic rotary position sensor. Instead of using light and a bunch of slits, this scroll wheel has a magnet mounted to it, and next to the wheel is a microchip that contains two magnetic field sensors, called Hall effect sensors, which are used to detect the magnetic field strength and the rotational position of the magnet. How do these sensors work? Well, in each sensor we have a very small plate of metal or semiconductor with electrons flowing across it. A basic law of physics called the Lorentz force is that all moving charged particles, such as electrons, are affected by magnetic fields. When moving electrons are introduced to a magnetic field with this orientation, they're deflected toward the bottom of the plate, or if we flip the direction of the magnetic field by rotating the magnet, they're deflected to the top of the plate. With the electrons concentrated at one side of the plate because of the magnetic field, we just need to add a few wires and additional circuitry in order to measure the voltage difference between the top and the bottom of the metal plate. As the magnet rotates, the electrons are pushed to one side of the plate and then the other, and the voltage flips from positive to negative and back again in a sinusoidal shape. This swing in voltage is then used to determine rotational speed and angular distance traveled. However, a single Hall effect sensor can't tell us the direction of rotation, and therefore, in this microchip, we have two Hall effect sensors, positioned perpendicular to one another and labeled X and Y. With two sensors, we're able to determine the absolute angular position of the scroll wheel because for every different angle, from 0 to 359 degrees, there's a unique combination of voltages on the X and Y magnetic sensors. The microchip over here records the exact angular position every thousandth of a second and compares it with the previous position. Then, using the difference in angles and the time between measurements, the mouse determines the speed, angular distance traveled, and direction of movement and sends it to the computer. There are a few things to note. First, the incremental optical encoder from earlier can't read out an absolute angular position because the wheel has 48 equally spaced spokes, and it can't discern one angle from the next. However, it is possible to have an absolute optical encoder which has a disc that looks like this, where different angles have different sections open to let the light through. It's also interesting to note that the physics of magnetic fields deflecting moving electrons, called the Lorentz force, is the driving principle behind all electric motors, just with coils of wires and different configurations of magnetic fields. Let's move on and look at two additional features. Here we have the scroll wheel assembly, below which you'll most likely find a push button. When you push down on the scroll wheel, it triggers the button. And when you release it, the plastic, or sometimes a spring, pushes the assembly back up. Most scroll wheels have some type of mechanism to create the clicking-like motion and sound as the scroll wheel rotates. A common way this is done is to have a ring of ridges, a spring, and a small plastic follower that rides along the ridges. When this button is pressed, the motor turns and rotates to engage the follower so that it presses against the ridges. As you rotate the wheel, the plastic moves up and down the ridges, thereby creating a stepped or chattering motion. And the spring applies a very light force so that the plastic follower stays in contact with the ridges. If you spin the wheel quickly, the plastic will continue to move up and down, and slow the wheel faster than if the follower were not pressing up against the plastic and the scroll wheel was spinning freely. One thing to note is that in this video we covered just two methods to measure rotational motion, an optical encoder and a magnetic position encoder. There are thousands of designs of computer mice and dozens of different ways to measure rotation. Other methods include a potentiometer, which uses a resistive track and a wiper that results in a change in electrical resistance. Older or cheaper mice use two push buttons and an attachment on the wheel that actuates these buttons. Additionally, there are different methods for registering a scroll wheel push and for creating different aesthetics when you rotate the mouse. For example, this scroll wheel uses an electropermanent magnet and teeth that conduct magnetic fields, resulting in the wheel stepping from tooth to tooth. There are many other designs that we didn't cover in this video, but if you have a broken mouse, we encourage you to take a look. Printed circuit boards, or PCBs, are everywhere, and inside this mouse you can find 4 of them. They may look complicated, but they're pretty fun to design, and purchasing them is made incredibly easy by our sponsor PCBWay. PCBWay can quickly manufacture your PCBs with competitive prices and impeccable standards. They also provide PCB assembly services, where they populate and solder the components to the PCB. The next time you want to get rid of that breadboard and take your project to the next level, consider using PCBWay to manufacture all your printed circuit boards. Thank you to PCBWay for sponsoring our channel and supporting engineering education. Check out PCBWay using the link in the description below. That's pretty much it for scroll wheels. This is the second video on the computer mouse. In the first, we explored the optical sensor and how computer mice take images of the surface and calculate X and Y movement. We recommend you take a look. We believe the future will require a strong emphasis on engineering education, and we're thankful to all of our Patreon and YouTube membership sponsors for supporting this dream. If you want to support us on YouTube memberships or Patreon, you can find the links in the description. Also, thank you to Logitech for providing information, reviewing the script, and providing a mouse to tear apart. Remember to subscribe, comment below, and share this video with others. This is Branch Education. Thanks for watching to the end.